Thanks very much for coming along. Today we're going to be, I'm going to be talking about, and this is another talk on microservice security. Earlier you may have seen Guy give a talk from a different point of view, more looking at the implications of security in serverless architectures, and also placing you more in the role of the attacker. This talk is a different type of talk. I've been looking into the area of application security, coming to it from the point of view of a conscious incompetent for some time right now, and hopefully going to be sharing with you some of the research I've been doing in the space of security in the context of microservices. When I'm not running tracks and talking, I also I wrote a book a few years ago. Has anyone here read this book? Some people. The rest of you can still buy it. It works really. You can get like a free subscription. If you go to Safari, the O'Reilly online thing, you get a free subscription for 30 days. You can read it for free. And then if you like it, like buy 5 copies for friends, family members. It's good as a bar mitzvah gift, giving out, your weddings, whatever you do. I also now run a company doing training and consulting and advisory work in this space. But we're really here to talk about security, because security is always interesting. Really, this sort of kicked into high gear, I think, for me, and I think for many of you. Probably you became more aware of implications around security and privacy post-Snowden, but it seems like every month there's a new teachable moment, which is great for a speaker like me, like Equifax, which we'll come to a bit later on. And we're finding bugs in our CPUs, which is of concern to many of us, especially when we suddenly start seeing our cloud instances running at 30% hotter because of new patches being made. And we've already touched earlier today on some of the challenges around things like the GDPR. And it's been interesting for me thinking about the implications of all of these ideas and these disasters and these forthcoming apocalyptic regulations onto a microservice architecture. We have this challenge though when it comes to things like security that we've got better, I think, as developers at thinking more broadly about what software development is. We've broadened our range of skill sets. We no longer just write code. We tend to talk in terms of, okay, we design the software, we develop it, we'll test that software, we'll ship that software, and we'll do these in faster and faster cycles, trying to optimize our cycle time, ship software more quickly. And then later on, we'll do some security later on. We'll bring some security in. It's almost like, a friend of mine put it, it's like do you want fries with that mentality? You spend you pick the nice meal you want, and so do you want some fries with that? And you go, yes, I'll have some fries with that. So basically, we hope that the security fairy will come and sprinkle magic security dust on your application after you've built it, and it's going to be fine, when the reality is it doesn't really work. But we have this mindset that we just abdicate responsibility. Our magic security experts are going to swoop in, and they all come, they all look different to you and I, and they talk different languages, and they'll do the magic stuff. The reality is there are an amazing great ecosystem of security experts and people who dedicate their lives to helping us build more secure applications. And there is a role for experts, that absolutely is. But we shouldn't abdicate all of our thinking around security to specialists, in the same way that we don't abdicate all responsibility for testing our applications to specialist testers. There is a role for both. The issue is, I think there's a very poor awareness about what is just enough security. With testing, we kind of understand where that line is. I actually think there's a lot of stuff that we could think about in terms of security that we could build into our applications and how we evolve our applications, that all of us as developers would lead to making a much more robust architecture. When we think about microservice architectures, we think about these independently deployable services, these things modeled around a business domain, these architectures which are all about autonomy and independent deployability. They actually give us some really interesting possibilities when it comes to designing secure applications. With a monolithic system, we tend to have everything in one place. All of our processing is being done within one process. All of our data tends to be stored in one place. That means when it comes to concerns around protecting the information, we have to protect the least important information in the same way as we protect the most important information. We can't easily sift and separate those things out. Classification of processing or data becomes much more problematic. With a microservice system, we get to separate things, we get to isolate things. We can focus our time and attention on those areas that need it. We can say, well, you know what? Actually, this is the place where my personally identifiable information lives, and that's where I need to spend my time, my energy, and my effort. This can be really useful when we start looking at some of the detail behind the general data protection regulations, for example. A lot of people, when I talk to them about GDPR, fixate on things like the right to be forgotten. It's going to be really hard for us to remove the information. What data can be safely removed when we worry about the right to be forgotten? That's not the most important thing for many people. Do you know what the most important thing is for a lot of people? Knowing what data you've even got. Microservice architectures can make that easier because you tend to get these boundaries that almost self-identify the data. It also makes it much easier for you to isolate your time and attention on those areas. It can make things like right to be forgotten easier to implement. We also have the ability to isolate services in different ways. We can deploy groups of services onto different subnets using network-level isolation, VLAN pairings, all those sorts of things to do defense in depth. So, you know, actually, Mark was talking earlier about this idea of the castle as the monolith. As someone who's looked at lots of castles, castles are actually all about defense in depth, and the microservices architectures work really well here. You have multiple walls to defend your castle, and you can have multiple perimeters to defend your microservice architectures. So at this point, you're all thinking that microservices plus security equals some giant love fest. Unfortunately, there are some downsides, because microservices giveth and they taketh away. And when it comes to security, they take it away in some quite nasty ways. Firstly, a lot of information that used to flow within a single process now is flying over networks between services. That was information which before was very hard to gain access to if you were a malicious attacker. Now anybody with access to your network has the ability potentially to get hold of that information, manipulate it, and do nefarious things with it. We also have much more points which could be attacked. So, you know, I might have a weak point in my system. There's no point in having a great, fantastic front door if your back door is made of balsa wood. And if you have a system where one of your points of attack is weak, that might allow an attacker inside your system. When you've got 5, 10, 15 services, maybe you can keep on top of making sure everything's patched. But when you've got 1,000, are you sure you've got no weak points in your infrastructure? You know weak points in your architecture? I actually think that organizations and teams with a poor awareness of application security will probably create systems that have more security issues with microservices than they would with a monolithic design. On the other hand, a savvy team who thinks about application security concerns could use a microservice architecture to create a much more secure system. It all comes down to whether or not you're conscious incompetence about security, in other words, you know that you don't know some things, or that you're unconscious incompetence, in which case you don't know that you don't know things. And I'm hoping to get some of you to at least know a bit more about this stuff. Let's actually start, though, with some real low basics, real basic stuff here. And some of this is a bit generic, not just in terms of microservices. This applies to application security in general, but let's start with some basic stuff. How many people here think they're very good at assessing risks? We've got one person. We've met the person who can assess risks. He will help you later. Okay, that's actually a good answer, because we are, as human beings, are really bad at assessing risks. So there's this fantastic report that comes out once a year from Verizon. It's called the Data Breach Investigations Report. It's thoroughly worth a read, especially if you care about application security. And in it, they look at the causes or the attack vectors used by attackers in the instances of a data breach. And you know, when I talk to people about microservice security, they start going on about transport security and encryption of databases and stuff like that. And I say, well, no. That's probably not what you've got to worry about. The single biggest cause, or the single biggest attack vector used by malicious parties in data breaches in Verizon's report is bad passwords. That's it. In 81% of all attacks looked at, and all breaches, these were actually successful breaches, looked at by Verizon, they found that 81% of this was due to either stolen or weak passwords. This is not a hard thing to do better at. It really, really isn't. So Troy Hunt, who's a security researcher, did a really lovely write-up actually summarizing good advice around about passwords and how you manage passwords. He was actually summarizing a bunch of information from people like NIST and the UK's own cybersecurity centre. And it's a great little, there's some real just real eye-openers here, which actually when you get down to it, are quite common sense pieces of advice that all of you would do better, would do well to observe. It's simple things like longer is stronger. How many people here have tried to create a password only to find that the website limits how many characters that you're allowed to use for your password? Because like disk space is really cheap, man. Like, why 20 characters? Are you high? I mean, come on, just throw some more disks at it. Long passwords are better. Allow people to create long passwords. This is an interesting one. Password schemes that have really complex character composition rules are bad. The reason? Because people struggle to create passwords within those constraints, and so end up, using arbitrary substitutions, like, A for the @ symbol, that sort of thing. And people have always been frustrated with sort of password schemes like this, maybe not potentially as extreme as this one, but no, we've seen stuff, right? It doesn't actually help. What we're trying to do is improve entropy. It can often be a lot better to have a long password with no special characters in it than a short password with some hard combination to remember that requires people to write stuff down or come up with easily enumerated attacks. Embrace password managers. How many people here are using a password manager like 1Password or LastPass? So, now keep your hands up if you're using it for your own personal use. That's most people. Right, now put your hands down. Now put your hands up if you're using a password manager for your day job. That's about half the people. That's a bit concerning, right? Some of you are using it for both, but probably half as many people are using it for your actual day job as your own personal use, and that's a bit concerning to me. Password managers are fantastic. They're great. A lot of the systems that we see out there, a lot of the customer-facing systems stop you using password managers. They do things like not allowing you to paste in password values because of security, which is often the response you get. This is an interesting one. Do not mandate password changes. This is weird. But my company makes me change my password every 3 months. Yes, they do. And they do this because they have a belief that means that if you have a password that someone gets access to, there's a reduced chance of them using it, right? If they got hold of a password you used 3 months ago, it's no good because they've made you change it again. What this actually does is two things. When you make people change passwords a lot, people come up with a password scheme that's just an enumeration. My awesome password 1, I've got to change it again. My awesome password 2. It's not really helping protect yourself. It's also tuning people to accept pop-ups saying, give me your current password, now here's a new password, password changed, which is an excellent way for phishing attacks to get passwords from people. Actually, NIST say do not require people to change their password. Instead, monitor and understand whether or not that password has been used in a breach or if we're seeing suspicious behavior and then require a password change. I mean, this is NIST. There aren't many more conservative IT groups in the world than NIST. And here's something smarter you can do now. You can actually start blocking previously breached passwords or identifying and telling your users that the password they are using may have been breached before. This is an issue because even if they've used that password and email combination, say, as part of the Adobe breach, if they're using that same email and password combination for another site, an attacker gets hold of that information, reuses that somewhere else. So another thing Troy's done as part of his Have I Been Pwned service, which is thoroughly recommended, he actually now makes available a set of hashes of all the passwords featured in basically all of the last large-scale breaches in the last sort of 5 years. This is a fantastic resource. It's very easy now for you to run through your, to generate hashes of your users' passwords, map them against this, and then tell your user, by the way, you need to change your password. 1Password have even integrated this into the web version of their product, and it'll be coming out in the new version of their desktop apps. So it will now tell you in the future, this password you're using was previously in a breach, you should change it. This is much smarter password credential policy than just automatically requiring you to rotate your own passwords for things. Let's roll forward a bit more. A couple of years ago, I think it was 2-3 years ago, this great post came out from Justin Smith talking about his viewpoint on how you defend yourself against one of the worst types of attacker. And that's something he calls the advanced, well, not he, but the security sector as a whole calls the advanced persistent threat. This is not your typical script kiddie. This is somebody who's probably targeted you. This is somebody who is sitting on your network. So an advanced persistent threat gained unauthorized access to a network and can stay hidden for a long period of time. Its goal is usually to steal, corrupt, or ransom data. This is someone who's got onto your network and is sitting there sniffing at what you're doing and is doing dodgy stuff, right? A great example of an advanced persistent threat would be something like what happened to Target. Target in the US had a massive data breach. Memory resident malware was installed onto the electronic point of sale systems. As credit cards were swiped, that information was captured. It was then exfiltrated out of that network after a period of time. That was a classic advanced persistent threat, something that sat around for a long period of time. Another great example of that would be something like the hack of the Democratic Party's emails, and in turn, the Dutch intelligence services hacking the Russian group that hacked the democratic services. The Dutch group had been sat up on the hackers for a couple of years, watching what they were doing. The Dutch group even managed to get control of the CCTV camera outside the offices of where the hackers were based and photographed every single person going into and out of the office, which is kind of freaking cool, right? This is the stuff we worry about. This is someone who gets in for a weak spot and then does not leave. How do you defend yourself against that kind of attack? Justin's advice in his blog post is it's quite simple, 3 key points. One is short-lived credentials. Now here we're not talking about the kind of passwords that we have for end users, we're talking about other types of credentials as well. We'll come to that back in a minute. The second thing is to patch your stuff. We absolutely are going to come back in that in a minute because we have to talk about Equifax. And finally, repave, which is just, if you're not sure, torch it, burn it all down. Now, that's easy to do if you've got fully automatable deployments, which you should all have building microservice architectures. If you've got fully automatable deployments and all of your software is built based on code that's in source control, and you don't allow for manual changes in your environment, and you've got backups, and your backups have been tested and worked, you've tested your backups, right? Hands up who knows for a fact, because they test them, that their production backups work. So that's like 10% of the room. All right, so room for improvement. Let's talk about short-lived credentials. Who here knows of a company called Codespaces? Hands up. Any Codespaces fans? There's one person. So Codespaces used to provide secure source code hosting, and they don't do that anymore because they don't exist anymore. Someone, and I don't know if they ever found out who, gained access to the root Amazon credentials for their account, and whether for fun or for malicious intent, wiped out their entire Amazon account. Now that's fine because you say that's okay because they've got backups, haven't they? Yes, they do. Where are your backups? They're in my Amazon account. Ooh, that's okay though because you've got source code backed up. Yes, we have. Where's that source code? In the Amazon account. So the whole thing was wiped out. Every single thing was in one Amazon account, right? This is a twofold problem. One, that credential that was leaked had way too large a scope of access. And so you always want to limit the access that a set of credentials gives you. Two, those credentials were still valid. It's now common practice for those of us doing things like using cloud providers to actually issue credentials that are time limited, maybe only living for 30 minutes at a time. That means if someone gains access to it after you've used it, there's a good chance those credentials are no longer valid. You've also got tools like GitRob, which can be quite useful. GitRob can actually scan source code repositories, Git source code repositories, looking for patterns of things that look like Amazon API keys. Nowadays, actually, both Amazon and GitHub scan GitHub, and you'll be alerted if your credentials are checked in. There's no guarantee that they'll alert you before you've been taken for several $1,000s worth of Bitcoin mining, though. But yeah, GitRob is a really good tool to run inside your own internal premises. People are always accidentally checking in source code into places that are more open than they should otherwise be. The problem with a microservice architecture is when we start getting into the world of wanting to rotate credentials and secure credentials, this becomes quite painful. Like we've got tens or hundreds or thousands of deployed services. You might have, say, 100 services, each of which themselves might be deployed 5 times. So that's 500 instances of a service where you might need to handle shared secrets, things like secret API keys for managing JWT authentication, for example. How do you manage that and how do you revoke that? There's two sort of problems here, when you have a time-limited credential. The first is, okay, well, it's expired, and the second is, how do I then issue the new token? Both of those are problematic. Think about something as simple as having a database. My running service instance needs to access data in a database. For it to do that, it needs to know what my username and password is. If someone gains access to that username and password, they can access my production data. And, this is bad, right? We have a problem here. A great way to solve this problem, and I think this is especially something you need to look at for sort of more fine-grained architecture where you've got lots of separate deployments, is to make use of some kind of secret store. There's lots of different versions out there. Guy touched on the fact that all the main cloud vendors provide some form of secret store or credential store. My own personal favorite is a tool called Vault, which is the best tool, I think, that's come from HashiCorp, which is saying a lot, as HashiCorp have done a lot of great stuff. But you've also got things like AWS Key Management Service and the parameter store and things as well. Vault has some really interesting capabilities. At a high level, it's a very simple idea. You have some application, could be your microservice, and you go to the Vault and say, please, can I have this credential? And to do that, you need to have some kind of authorization token. Now, that auth token can be, again, itself time limited, and it could be scoped just to your credentials, and that's typically something you'd have to bootstrap the application with. But you could bootstrap that effectively memory resident, so it's very hard to gain access to that token. And again, that token, there are ways of expiring that token. That then allows Vault to go and fetch the information you want from a physical backend, and Vault will encrypt that data as it's stored into the backend. It reads that data out of the backend, decrypts it, and hands that over to you. Normally, people use some sort of physical backend like XCD or console, something like that. There's a kind of interesting thing here, which is the Vault process itself. When you launch one, you need to have this process of unsealing it. What that kind of mean? Well, conceptually, what we're doing here is we've got lots of really important keys, and we're putting them in a box. And then we're locking that box so we don't let other people get hold of those keys, right? Conceptually, that's what we're doing. There's a problem with that, right? We've locked the box with a key. Where do we put that key? In another box? Do we then lock that key and then put it in another box? Well, actually, we do. There's another problem here, which is that key that locks that box is really important. It's now the key that theoretically lets you get access to lots of other pieces of information. There's an algorithm that Vault uses, which is really quite cool, which says, well, the problem is there being one key. So let's have loads and loads of keys that you could use to open the box. And what we do is we rely on a quorum of those keys being available to unseal that vault. So there's an algorithm called Shamir secret sharing. So in this example here, we might have 5 keys available that could be used to unseal the vault, and we might say we need at least 3 of those to actually open and unseal that vault. And that's something you just have to do when you launch the vault process. This is the only sort of manual process involved with this. So when I was working at a startup about a year ago called Atomist, we had a running Vault instance for managing our secrets, and so we would store our keys to Vault would be stored in our own individual 1Password accounts. Even if someone gained access to my key, by itself, that's not enough to open up that vault. One of the things that Vault does that's really, really cool, and there's a lot of cool stuff it does, is handle time-limited passwords. So if I want to, for example, have a username and password for a database, or maybe I want to get API credentials for, say, Amazon, Vault will handle this for me. I can go to Vault, say, give me a set of database credentials. It will talk to Postgres, in this example, on my behalf, create maybe a one-time or a 15-minute limited username and password, and will pass that back to my application. And if those credentials get leaked, they're only valid 15 minutes, and it will tie it underneath. And you can even use that to provide and issue credentials to real-world users. One last trick under Vault's sleeve is that it actually works really well with a tool called Console Template. So Console Template does a very, very simple thing. It updates values in text files with values in Vault. This becomes quite useful, especially when you've got legacy software or software that's just configured by text file. You don't have to update that software to suddenly talk to Vault, but it wants to read information from a text file. No problem. Console Template can take a template like this, and based on values inside Vault, actually fill in those username and passwords for you. So as they change and as they expire, it can automatically update those text files. Very, very cool tool, and a great way of rolling out secrets across your system. It's far from the only mechanism you can use, but it's worth looking at. Let's take a look at another basic thing here. This is another report came out from Forbes BMC back in 2016. They showed that 44% of all security breaches occurred after vulnerabilities in solutions have been identified but not patched effectively. Okay? This brings us to Equifax. Equifax, as you may know, was breached due to a problem in a version of struts that they had. So basically, if you dive into it, there was a particular vulnerability inside struts which allowed this malicious party to gain access to a large quantity of data. We dive a bit deeper into that particular patch. We find that it had a very, very high impact score. This is on the CVSS base. Now, I don't really understand this very much, but what I did look into, that number 10, that's interesting. That score, by the way, that impact score for this vulnerability, that's not out of 100. It's not out of 50. It's not out of 11. It is out of 10. And that means that 10 is very, very bad. Now, this stuff went, actually, this CVE went public in March, basically early March 2017. I can't get the exact date. But the patch was already available in struts on March 7th. If you look at what happened with Equifax, we know the breach happened between mid-May and July. We don't know exactly when because they're not sure when, because that's the nature of these sorts of attacks. You're not entirely sure when it happened. They spotted it on the 29th of July, that we know. It took them a rather long time to tell anybody about it. This is not on. All right, getting hacked is bad. Waiting that long to tell people around the world that you've leaked critical information about them is very bad. So at best case, assuming that the attack happened quite late on in that window, they still had at least 2 months between the patch being released and the attack happened, and potentially as long as 4 months to roll out that patch. And people go, oh, bad Equifax, bad Equifax. We're talking about a 2 to 4 month window. So 2 to 4 months, that's the window they had to apply this patch. Hands up if you know every single one of your systems is patched every 2 to 4 months. Put your hands up. Yeah, we've got like 6 people. Oh, there's a few more down here. Very smart people. This is the problem, right? This is another thing from the Verizon report. Patch cycles are getting better. Organizations as a whole are getting better. Sector by sector, it's not great. Education sector, still not great. But generally in the IT sector, we're getting to a good patch saturation cycle. These are the timeline along there. We tend to fix a lot of stuff very, very quickly. Like this is showing 50% of all bugs fixed, almost immediately. This is through auto-update cycles and the like. And there's a long lag. Very few people get up to 100% of these vulnerabilities being fixed. There are reasons for this. Often the vulnerabilities can be fixed in other ways than applying a patch. But we're now in a world of this sort of nesting doll deployment type systems, right? We have, let's think about a traditional stack diagram associated with the deployment of our software nowadays. We're running on Docker or Kube or something like that. We've got our hardware, we've got our operating systems. On top of that, we've got our hypervisor. On top of that, we've got our virtual machine. Then inside our virtual machine, we're running Docker. This is sort of the stack diagram you'd have if you were running, say, a Docker process on an Amazon instance. Your Docker process is running a container. Your containers is running a container operating system. That container operating system has your application on top of it. And every single one of these layers, every single one, needs to be patched by somebody. Somebody, somewhere, needs to be doing this for you, okay? We had about maybe 10 people who were convinced that they'd patch all of their systems that they manage every 2 to 4 months. So I'm going to ask the same question again. Now, with that in mind, how many of you know, and the question is know, that you patch in between 2 to 4 months? We've got one hand up. Right? This is the thing, right? It's very easy to be saying, oh, that our Equifax crap. And the reality is any single one of you could be a new Equifax. What can we do about this? Well, the world's not quite as bleak as I make out. The reality is, if you're on a cloud vendor, they're going to handle a lot of this for you. Even if you're just working at the level of abstraction of, say, infrastructure as a service, they're going to handle looking after patching the chips, which needs to happen, and has been happening recently, managing the underlying operating systems, rolling out changes and patches to the hypervisors. Those of you running on Azure, Google Cloud, or Amazon, for example, you would have had all the meltdown and Spectre bugs patched within days of that stuff being made public. That was done for you, right? You don't have to worry about that stuff. If you're running, say, a higher abstracted platform like a container orchestration as a service, maybe you're running EKS or ECS or some kind of managed Kubernetes cluster, Again, there's more stuff is being handled for you. They're now managing the rollout of your Kubernetes nodes, patching those sorts of things. So you actually only have to focus on the stuff up here. You're now just looking at the container operating system level. You're now only having to worry about your application. This makes your life much, much easier, right? True, you've got to trust your cloud vendor, but then you kind of have to trust your cloud vendor anyway. You're running on their hardware. If you don't trust them and you're running on their hardware, you need your head examined. When we start to higher level abstractions, we're looking at function as a service, sort of platform-based, more platform-based compute. You've got an even smaller surface area to look at. Think about something like Lambda or Azure Cloud Functions. You're actually now just focusing your time and your attention on the function itself. So if you're in, say, a container-based deployment world, we've got tools out there that can help give us visibility into our patch health. We've got things like Claire from CoreOS, which does layer-based scanning and can look for vulnerabilities in layers and containers. And we've got other sort of commercial tools being built on top of this. You know, Equifax, for example, have got this lovely tool that shows you which vulnerabilities you've got in which you're running containers. That's really useful. Not just looking at, you know, the problems in your registry, but also looking at the running systems. What vulnerabilities do I have out there in the live? One of the challenges associated with these finer and smaller grained architectures is often once we've created a bit of code that does a good job, we don't need to touch it again for quite a while. That might remain untouched for months or maybe years because it does what it needs to do. That means we may not get around to patching it or updating it in any way, shape or form. And I worry if this is going to happen with serverless as well. When we come into the space around application development, we've got tools like Snyk, which I'm a big fan of. Snyk will just look at the dependencies of your application code, and it will tell you when you're depending on libraries which have known vulnerabilities in. It will even go further and will actually say, oh, here's a pull request, so you can just actually update to the newer versions, and so basically I'm going to help you patch it for you. I think when tools like this exist, and they are cheap for what they do, I told Guy he should raise his prices, there is no excuse actually for not being better at this. There is still an unknown, there's a bit of a challenge here, certainly around function as a service. This is a build and sort of source code analysis technique. It doesn't yet work runtime because we don't have access to your third-party dependencies in a running fast platform, at least we don't with Lambda. The reality is you also, though, need to think rationally about what your risks are. I've given you some data from generic sources that are looking at large industry sectors, that Forbes BMC report, the Verizon data breach report. But every organization is a bit different, and your context you operate in is a bit different as well. Therefore, making rational assessments about where to protect your application becomes difficult unless you've done some kind of threat modeling exercise. Now, this is a great place to get an actual expert in to help you look at and assess the risks your application faces. If you want to do it yourself, I thoroughly recommend the stuff that Microsoft have up on their secure development lifecycle. There's packs and packs of great information there. And look, you're not going to do as good a job as a conscious incompetent like myself running yourself through this process, but it may well be a good start and might help you focus on the right things. Let's talk about some more interesting stuff now. Let's actually talk about the things that people want to talk to me about application security around. Specifically, we should talk about transport security. I've been wanting to use this slide for ages, right? This is the real cool, sexy stuff for some value of the word sexy. I happen to think that Jason Statham is one of the finest actors working in cinema today. My wife thinks I've got a man crush. It's not true. He's just gorgeous. Anyway, we're talking about a microservice architecture, and this is the question, how do we protect things at transit? This is where stuff gets interesting. Let's take a look at an example, little architecture here, and think about the different challenges we've got. I've got a few services that exist within my own service perimeter, right? These are the services that we own, that we develop. We have consumers that are running out of band. They're accessing our site and accessing our information. And we maybe have some protected third parties downstream who we're sending secured information. As an example, I'm sending royalty data because I'm now doing music streaming. I'm not just selling CDs like I used to. I'm now streaming music. We're going to be the new Spotify of Hackney. And so this is going to be great, right? We've got lots of different concerns we have here around transport security, those lines that flow between all of these things. The concerns we think about, we're looking at things like observing data. Can people see the information we're sharing? Is the data we're sending between services being manipulated by somebody? How do we restrict access to endpoints? You know, it's a client-based auth access. And can people actually impersonate endpoints? Could someone hack into your network and launch their own payment service version and now start absorbing all of your payment requests and siphoning off money? It's actually quite a hard attack to pull off, but it's quite devastating if they manage it. And of course, we should talk about the basics, we should talk about the easy stuff, we should talk about something like HTTPS anywhere, right? Really, we mean here HTTP and TLS. So this is great. We get server guarantees. We know who the server is. We know the payload has not been manipulated. Client guarantees get kind of interesting, right? How do I know who's accessing my server? But out of the box, typical HTTPS is about server guarantees. It's about the server I talk to is the server I think it is. Client management has traditionally been challenging here. Again, though, this is no real excuses. We've got things like Let's Encrypt, which is not only free, but it's also fully automated, a way of generating short-lived certificates. They're even going to start offering wildcard certificates shortly, which is something that many people saw as a bit of a pushback. But I suspect many of you are on Google Cloud or Azure or Amazon. Every single one of those platforms now makes it easy to issue free certificates with a fully automated workflow around that. They even have support for doing things like installing those in their various API gateways. If you're communicating over some sort of HTTP-based protocol, there is no excuse for not doing that if you're on one of those cloud vendors. This is not hard stuff. This solves part of the problem for us. It helps stopping people observing our data. It stops people manipulating our data. Restricting access to endpoints, and it stops people impersonating endpoints, assuming you actually validate your certificates. So, yeah, great, obvious choice. It's obviously an obvious choice for the public internet as well. Browsers will soon start marking sites as being insecure if they don't support HTTPS. Let's knock it up a notch. Let's talk about mutual TLS. So mutual TLS actually implements, is an optional part of the TLS protocol which allows clients to also identify themselves through some kind of certificate. And so here we now get client and server guarantees. But certificate management is even more painful in this area, typically because we have more consumers than producers, although in a microservice architecture I think that actually balances out. Again, there are solutions out there to solve this problem. Azure has great support, for example, for issuing client-side certificates and installing them in the API gateways so that actually your application doesn't need to worry about installation and management of client-side certificates anymore. AWS can do exactly the same thing. So if you're on those platforms, do not complain to me, oh, Sam, it's really, really hard. Then you don't deserve to have a system, okay? So mutual TLS is fantastic. Observation of data. We can't do that anymore now. We've got guarantees that people can't sniff our information. The data cannot be manipulated. We protected ourselves from man-in-the-middle attacks. We've restricted access to the endpoints, and we've stopped stopped impersonation of the endpoints. Fantastic. The issue, of course, and this is this might make sense, lots of different places. Not for the public web, right? You don't want your clients to start managing certificates, but maybe with trusted third parties within your perimeter. The issue, of course, is there are lots of protocols out there that are not HTTP, and they're not running over synchronous TCP calls. A lot of people, yes, they're using HTTP or gRPC or some other protocol, but lots of people are using things like message brokers. And here, if you want to do something like mutual TLS, you're going to have to look at the protocols provided and supported by your vendor of choice. Both RabbitMQ and Kafka both support varying levels of protection, both client and server-based authentication. Rabbit does support TLS for out of the box. Kafka's had a pretty rich support for this stuff since as far back as 0.9. The Rabbit stuff does involve installing an Erlang module, which is the sort of thing that your sysadmins do not like being told. But anyway, it can be done, right? So we've got transport-based authentication to an extent, right? We've got client and server guarantees. The server knows that the client talking to it is the client it says it claims to be, and the client knows that the server it's talking to is the service it's supposed to be. Right? Server-side identity is guaranteed, client-side identity is handled. This is service-to-service authentication. These are computers talking to other computers. But we exist in a more complex world than this, right? We exist in a world with real human beings. We have mobile devices, we have web browsers, we have humans that need to access our systems. So along they come and they need to gain access. And actually the world here of how we handle your identity and what you're allowed to do is pretty straightforward, okay? We're probably going to use some kind of auth gateway, and then you're going to use something like HTTP-based basic auth, or more recently, we'll be using something like OAuth, certainly for mobile devices, increasingly for web-based authentication for real people. Typically here we're talking about something like OpenID Connect, which is a subset of the OAuth 2 framework. This is all pretty straightforward and nice and easy. But this is an interesting thing. So this is primarily when we talk about sign-in, we say, I've logged in with my username and password. This is an authentication issue. You are who you say you are. The next question is, what is it you're allowed to do? Things get funky here. So here we are in a situation, and someone comes along and says, I'm Bob. And the auth gateway says, are you really Bob? And the Bob goes, yes, and I'm going to prove it by giving you a username and password. And the auth gateway is going to go, okay, I've checked that, and you really are Bob. You are now logged in, and you can now talk to the music web shop to maybe look at your details, okay? This is not rocket science. This is quite straightforward stuff, I hope. We get a nice big tick, and there's a smile on our faces. Everyone's happy. The reality, of course, is we don't have one thing we want to talk to. We have lots of things that we want to talk to. Because really, what Bob wants to do is Bob wants to see his details. He wants to see his account page. But the information about Bob is actually stored in a service called the user service. So what happens is, I want to go and see my user data. Maybe I click on the profile link on the website, and I go along to /user/Bob. And I go to the auth gateway, and the auth gateway lets me in because I'm signed in. There's some sort of cookie probably being dropped. And the request goes through to the music web shop. And the music web shop goes, I don't have that information. I know where I can get it from. It goes and talks to the user service and says, can I have Bob's details? And the user service goes, well, I know who you are. You're the music web shop. We're buddies. I trust you because I've seen your certificates. I mean, this is where the anthropomorphization of the services breaks down a bit. But anyway, I trust you. We have an implicit trust model. The user service says, yes, of course you can, because I trust you, the service. Here is Bob's details. Then Bob's details get sort of rendered up into a nice HTML page and then sent back to the client, and now Bob has his details and the world is good at this point. Let's take it a bit further. Bob gets some funny ideas. He looks at the URL scheme and says, oh, what happens if I just take the word Bob out and put the word Alice in? Can I get Alice's details? The request comes into the auth gateway. The auth gateway just says, are you logged in? Yes, you are. Okay, off you go. You go to the music web shop and you say, can I have Alice's details? We know the music web shop doesn't have it. It has to go downstream. Can I have Alice's details? The user service goes, well, you're the music web shop. I trust you. And it fetches Alice's details and renders a nice web page. And now they're accessible to Bob, which you wouldn't think is the right thing, would you? This is actually the example of what is sort of application security called the confused deputy problem, right? Where we've tricked an intermediary party into asking for information they shouldn't be able to ask for. We've had this implicit trust model, and we haven't actually applied any authorization controls. We haven't said, what is it that Bob is allowed to do? What we really need to do is think about authorization of what Bob can do, but the question then is, where is that authorization? We could choose to do authorization upstream, maybe inside of our auth gateway, or maybe in our edge service. The issue with that is, all the capabilities that our system provides is actually split up into lots of different services. Is it really valid that I should be able to make decisions upstream about what capabilities exist downstream and know what things you can or can't do? If you want to authorize things up at your auth gateway, it pushes you into a centralized model of permissions management. But then every time I roll out a new service that adds a new capability, I've got to also update how the authorization happens at the front end. That feels a bit backward to me. The reality is, I think, and this is more in the spirit of microservices, it's much easier in the service itself to make valid decisions about what somebody should or shouldn't be able to do. The issue in this example, though, is that the downstream services don't know who the request is being made on behalf of. If it could be told, by the way Bob's asking, it might be able to make much more valid decisions about what can happen. So ideally, when we have a system, we want the user service to say, no, I know it's not correct in this situation for me to give you Alice's information because you're Bob. But at the moment, the only place that has that information is the auth gateway. One way of solving this is use something like JWT tokens. It's become quite popular. Quite a simple idea. You basically take a JSON little JSON payload like this, and you generate a hash of that payload. And that has a number of different, it's sort of quite like HMAC if you've seen anything like HMAC before. And then you send that information along, and you can actually also optionally encrypt the token as well if you'd like to, but typically you just send the token over some kind of protocol which is already protected, much like you'd put a cookie over HTTPS. You then pass that information along in the header, and then the downstream service can actually validate the hash using some secret key that has to be communicated out of band, validate that that token that's been given really is true, and say, oh yes, you really are Bob, you really are Alice, and maybe even have information in that payload regarding the groups that that person is in or the permissions that that person has. You can put quite a lot into a JSON token within limits. So in this situation here, Bob is logged in, and Bob has some sort of, might be an OAuth token, right? So the auth gateway needs to be able to exchange with that OAuth token. This is typically how most people seem to implement it. They use sort of standard OAuth upstream. They then map the OAuth token into something like a JWT token, which might have additional information about that user that you might not want to leak outside your perimeter anyway. So that token can then be passed downstream. So our token is very, very simple. It has user Bob, right? The music web shop makes that call downstream, says can I have Alice's details. The user services logic is such that if it's asked for someone's user details, you can only give it the details of the person who's asked for it. And it says, no, you're Bob, go away. Optionally, you could do something like here, have a group that said admin, and then the logic in the user service could be if your user is Bob, or you're in a group called admin, or so you can see any data, that sort of thing. So kind of cool stuff. No need for a round trap in that world either. I want to leave you with one last thought. Service meshes are all the rage. There's a bunch of these tools out there right now. Linkerd and Istio are probably the most popular of these. One is ready for prime time, one is not. I'll leave you to guess which one. Service meshes are quite interesting tools. They actually centralize a bunch of concerns. Historically, we have a whole load of stuff that we have to do inside our application that is kind of boring to do, right? Let's think about the common concerns in a microservice architecture. We've got things like tracing, right? Managing tracing, that's common code I've got to manage in there. Load balancing and service discovery. I've got to add things like authorization and authentication, the stuff we've just been talking about, all that code to manage those JWT tokens. Maybe even manage things like certificate management inside that sort of stuff. And also typically we do things like connection resiliency and retry mechanisms. And that's kind of, right, that's useful, but that's annoying to have to repeat that over and over again. And what happens if one service implements it in a bit of a different way? I mean, sure, you can use common libraries like Spring Boot, but what happens if you're in a sort of polyglot environment where you've got different technology stacks? What happens when you've got different versions of that library being used for sort of capabilities that need to be enforced consistently? You don't want a weak link in your chain sort of creating a space where a security attacker can get in. You might need to control that more centrally. This is where service meshes come in. They sort of take this idea of having a local proxy that implements all that common logic. So in this example, this is kind of more of a proxy model, what's called a sidecar model. I've got lots of services locally, and they want to talk to another service. They actually go through this central proxy. That proxy will then allow you to talk to other services. And then that proxy layer, you can do all kinds of interesting things like certificate management and implementation of mutual TLS, JWT token management, and all those sorts of things. And then you have like a control plane that lets you manage all of those things. It's a really, really interesting idea, but this space is super new. There are different deployment models out there. Istio is getting all the hype, but it's still not production ready, unfortunately. If you're interested in using something like a service mesh to simplify this, do take a look at Linkerd because it's actually a bit more tried and tested. But even Linkerd are now re-implementing their idea of a service mesh, moving to things like Conduit. I think service meshes in the future might really simplify some aspects of our transport security play. I think we're perennially looking at about 6 months out. Any day now, they'll solve all of our problems. Now, we've covered quite a lot of things, so I have unfortunately run out of time, but I'm going to hang around for questions. But thank you so much indeed for your time and your attention.